everyone, I am Madhvi Gaur, Assistant Professor ABES Engineering College. Today I am going to discuss about AVL tree. I will tell you how we can perform or we can insert an element into an AVL tree, as well as how we can delete an element from an AVL tree. First of all, we will understand what we mean by AVL tree, or how can we define an AVL tree. An AVL tree is a height balance tree. It is known as a height balance tree. And what is the meaning of height balance tree? A height balance tree is one in which the difference in between the height of the two subtrees, which is left subtree as well as right subtree, for any particular node is not more than 1. It means if I want to calculate the balance factor of each node, then it will be given by height of left subtree minus height of right subtree. What we mean by this? Let us understand through an example. Let us consider this is a binary tree. And I want to calculate the balance factor of each node. Then it will be given by, we have to calculate it from the bottom to top manner. First of all, I will calculate the balance factor corresponding to this node. It will be given by height of left subtree minus height of right subtree. As this node does not have any children, left child is 0 as well as right child is 0. So it will be given by 0. Similarly, for this node, it will be given by 0. For this node, if I'll calculate, then it will be given by left subtree minus right subtree. Left is 1 and right is 0. That's why it will be given by 1 minus 0, which will be 1. Similarly, it will be given by 0 minus 1 because 0 is left child and 1 is right child. And as per the definition, it will be given by left minus right. So it will be minus 1. And the balance factor corresponding to this root node, it will be left subtree, which is 2, minus right subtree, which is 2. So it will be given by 0. So height balance tree is in which we have to calculate the balance factor of each node. If I want to know whether a particular AVL tree is balanced or not, for this, there are only 3 values which are allowed. That will be 0, plus 1, and minus 1. If the balance factor corresponding to each particular node lies among this value, then we can say our tree will be balanced. Our tree will be balanced. Other than this value, if we got minus 2, plus 2, or any other value other than this value, then our tree will be unbalanced. And if we will examine that our tree is unbalanced, unbalanced tree is which tree? Which particular node has out of these 3 value, other than this value, if there will be noted, then we can say our tree will be unbalanced. So for making our tree balanced, we have to perform certain rotations. For performing the rotations, first of all, we can see into the next slide. As if I want to insert a particular element into an AVL tree, then it will be similar to our binary search tree, which I have discussed in my previous lectures. After inserting an element into an AVL search tree, the result may not be an AVL tree. It means a tree can be unbalanced. If a tree becomes unbalanced, then it needs to be adjusted. And how we can adjust? We can do this adjustment by through rotations. So basically there are 4 types of rotations that are left-left rotation, right-right rotation, left-right rotation, and right-left rotation. Let us understand all these rotations one by one with the help of an example. First of all, we will discuss LL rotation, which is left-left rotation. Let us consider some example. I'll consider a binary tree. Let us assume 18, 16. And I want to insert a particular element into this AVL tree. And that element is, let us assume I want to insert an element 12. Then, as I know, BST AVL also follows the concept of binary search tree, while in the case of insertion as well as deletion. For inserting an element which is 12, I have to analyze or compare this with 18. So 12 is smaller. That's why 12 will go to the left side. Again, there is some node which is 16. 12 is compared with the 16 and it will be inserted as a left child of 16. Now, for calculating or to see whether our tree is balanced high tree or not, we have to calculate the balance factor of each node. As in my previous slide, I have already discussed that how we can calculate the balance factor of each node. That will be given by height of left subtree minus height of right subtree. Okay, then I'll calculate for this node. It will be 0, it will be +1, and it will be +2. Now I can notice this particular binary tree, this is balanced, but at this node, it is not balanced because this value is other than 0, +1 and -1. So this tree needs to be adjusted. So for performing this type of rotation is known as LL rotation. In LL rotation, which is left-left rotation, we have to perform a single right. We have to perform a single right, and but from where, at which node where it is unbalanced. So please make a note of it, at which node where the tree is unbalanced, only at that point we have to or we need to perform the rotation, which is a single right. So at this point we have to perform a single right operation. Then after performing this single right rotation, our tree will look like this. 16, 18 will move towards right child of 16 and 12 will be as it is. Now again, I'll calculate the balance factor of this particular binary to see whether it is balanced right now or not. So now we can examine this tree has become balanced because all the values are lies in between 0, +1 and -1. So this type of rotation is known as LL rotation, in which we have to perform a single right operation. Okay. Now let's see another rotation, which is RR. Let us examine another example, 18, 20, and now I want to insert a new node which is 22. Then for sure 22 will become the right child of 20. 18, 20 and 22, because we know the BST property in which the root node value will be less than its right child. That's why 22 will be placed here. Now again I'll calculate the balance factor of each node. It will be -2. This type of rotation is known as RR rotation, and in this we have to perform a single left. But at which point we have to perform a single left? Where it is unbalanced. So it is unbalanced at this point. That's why we have to perform a single left rotation at this node, which is 18. Then it will be look like this: 20, then 18, and then 22. Again, we will check whether it is balanced or not. Then we have to calculate the balance factor of each node, which will be given by this. So this type of rotation is known as a RR rotation or right-right rotation, in which we have to perform a single left. Okay. Next rotation is left-right rotation. Let us consider an example. 18, 16, then I want to insert a node which is 17. 17 is less than 18. It will go to the left. But 17 is greater than 16. That's why 17 will come here. Now I'll calculate the balance factor of each node. It will be given by this value. Now we can notice there is a sign change. From negative, we are moving towards the positive points. It means we have to see at which node, after inserting which node, our tree become unbalanced. So I can notice when it was 16, the tree was balanced. But as soon as I inserted the node 17, our tree become unbalanced. So we have to follow that path. This is at left side, and this node is placed at right side. That's why this type of rotation is known as LR rotation. And in case of LR rotation, as this node part is heavy, which is at the right side, okay, so we have to perform the rotation in the opposite direction. That's why it will involve the left rotation. And here we can see this part is left and we have to perform the rotation in the opposite side, which is our right side. So which one have to perform first? We have to follow from the bottom to top. So first of all, this type of rotation will be performed in the first step. And the second step, we have to perform this rotation. Then the tree will look like this in the first rotation, as we have to perform the first part. Then it will be as 17 has to move towards left side because we have to, this right part is heavy. If right part is heavy, then we have to shift it towards the left. Then the tree will look like this. After moving towards left side, it will become like this. Then this was the first rotation at the first point. Now we have to involve the second rotation, which will be done at this point. Then the tree will become, now we have to see this left part is heavy. Then we have to rotate into the opposite side to make it balance. Then tree will be, then 17 will become the root of the tree. 18 will go to the right side and 16 will become the left child. Then again, I'll calculate the balance factor of each node. Then we can see that the tree has been balanced now. So this type of rotation is known as LR rotation, which is left-right rotation. Okay. Now let us consider the next example. 18, 22. Now if I want to insert a new element, which is, we can assume 20. 20 is less than 22. That's why it will has to be added at the left hand side. Again, I can see after inserting 20, my tree has become unbalanced. This will be +1 and it will be -2. Again, we can notice the sign change. We are moving towards plus to minus. Okay. So after inserting this 20, our tree has become unbalanced. So we have to make the adjustment. So this part is the left part. So as we have discussed earlier, which part is heavy? Then we have to perform the rotation into the opposite direction. Then it is left. Then we have to perform into the right side. And in this, we have to perform into the left side. Okay. So this is R and this is L. That's why this rotation is known as RL rotation. We have to perform first this rotation from the bottom to top and then this rotation. Then the tree will look like 18. This left part is heavy. Then we have to perform into the right side direction. Okay, left part is heavy. That's why we are moving towards the right. After moving towards right, the nodes will be shifted. It will become 20 and it will become 22. So first part rotation has been done. Now I'll talk about second. In this, we have to rotate it into the opposite direction. It will look like this. 20 and then 18 and then 22. Again, I'll calculate the balance factor of each node. Now I can see now tree has been balanced. So this was the RL rotation, which is right-left rotation. Now let us consider an example for inserting a new element into a AVL tree, which is very important topic as per the university criteria. So there are following elements which I need to insert into a balance height tree. Let us consider first I have to insert 64. So there is a single root child which is 64. I have to calculate the balance factor which is left minus right. As there is no left child, no right child, it will be 0 minus 0. That's why this balance factor is 0. Now I have to insert 1. As I know, 1 is less than 64. That's why 1 come at the left child. Okay. I'll calculate the balance factor of it. It will be 0 and it will be 1 minus 0. That's why the balance factor is 1. T is balanced at this situation as well. So there is no need of rotation. Now I have to insert new element which is 14. As 14 needs to be compared with this, it will go to the left. Then 14 needs to be compared with 1, it will go to the right. Now I'll calculate the balance factor of each node. It will be 0. It will be left minus right. That's why it is -1. Then again it will be, for 64, it will be left minus right. So in the left, there are 2 children and in the right, there is no. That's why the balance factor is 2 minus 0. That's why it is 0. Now I have to see which part or which edge is heavy. Then after inserting 14, this part become unbalanced. So I have to move, see from the 2 which is unbalanced and this make a direction. This is L and this is R. That's why this type of rotation is known as LR rotation, in which we have to rotate in a 2 steps. First, this needs to be rotated and then second, it needs to be rotated. Then after rotating this step, then 14 will become the root node of in place of 1 and 1 will go to the left part of this. That's just like this. 14 will become the parent and 1 will become the child of it. But only the first part has been done here. Now I'll talk about the second part in which the rotation needs to be done like this. Then 14 will become the root node of this tree, and 64 will move to the right side, and 1 will become as it is. Okay, that's why this tree has been converted after LR rotation into this form. Then we have to calculate the balance factor of each node. As in the diagram, we can see or we can analyze all the nodes are balanced. Okay. Next, I have to insert 26. As we know, we need to compare with this, it will go to the right. We need to compare with this, it will go to the left. Again, I'll calculate the balance factor. Now I can see there is no unbalancing. Then I'll insert 13. Then 14, it will 13 will go to the left, and for this node, it will go to the right. Again, I'll calculate the balance factor. I can analyze key this is balanced tree. Then I need to insert 110. Then it will go to the right child. And then for comparing with 64, it will go to the right child. That's why 110 placed here. Again, I'll calculate the balance factor of each node. As through the diagram, I can see all the nodes are perfectly balanced. Okay. Then 98. Then it will go to the right. It will go to the right. But for 98, it will go to the left. Then we will place the 98 element as here. Again, I'll calculate the balance factor of each node. As I can see, this tree is right now balanced. So no need for further rotation. Okay. Now I'll insert the new element, which is 85. For 85, it will go to the right. For this, it will go to the right. For this, it will go to the left. For this, it will go to the left. Then 85 will come here. Okay. Now I'll calculate the balance factor of each node. We can see this here the unbalancing is done, here is unbalancing, and here is unbalancing. So which needs to be followed first or solved first? So we have to make a note of it that we have to perform from the bottom to top. If I resolve the problem of the bottom subtree, then might be the upper subtree's problem will automatically get resolved. So no need for concerning about these minus 2's. We have to concentrate only this part, which is where the first unbalancing is done while we are moving towards from bottom to top. So we have to resolve this problem. As I can see, after inserting 85, this path has become unbalanced. So we have to perform or we have to balance this part first of all. Okay. So we have to see 85 lies at the left part of it. So that's why LL type of rotation will be done. In LL type of rotation, single right has to be performed. So we have to perform the rotation like this. Till this point, all the nodes will be as it is. I can mention here as well. Till this point, all the rotation part will be same. We have to perform the rotation only at this part. Okay. Then 98 will become the node and 110 will become the right child of this 98. So 98 will move upwards, 11 will become the right child of it, and 85 will be like this only. Then we have to again calculate the balance factor of each node, and I can see here now my tree is perfectly balanced. Tree is balanced now. So this was the concept related to insertion into an AVL tree. I hope you people got the concept related to it and all the rotations which I have discussed in this lecture. Next, we will focus on the AVL tree deletion. So before performing the AVL tree deletion, let us understand this. First of all, I'll insert all these elements, then I'll perform the deletion one by one. So we have to insert all these nodes first. 17, then 12, then 21. I'll also checking whether this tree needs to be balancing or not. We can see this. I'm calculating balance factor at each step. So this is balanced right now. Then 10 will come. 10 will come here. It is right now balanced. Then 90 will go here. It is balanced right now. Then 15 will come here. It is balanced. Then 27 will go to the right part. Then it will balance right now. Then 14 will come here. Then 16 will come here. Now I'll calculate the balance factor of each node. It will become -1, 0, 0, 0. It will be 1, 2, 3, 1, 2. It will be +1. So our tree is balanced. So it do not need any revision of or any type of rotation right now. But we will see when I want to delete any element, then it needs a rotation or not. Okay. First of all, I'll check whether it is correct or not. 17, 12, 10, this is 15, this is 14, 16, it is okay. 21, then 19, and then 27. Yes, our tree is perfect. Then first of all, I delete first element, which is 10. I want to delete 10. We have to look whether 10 is present inside the tree or not. That's I want to first delete this 10. So I'll write down the statement here. Delete 10. After deleting 10, before deleting 10, we have to see whether this 10 is a leaf node or it has a one child or it has two child. So we have to consider all the BST deletion cases here as well. But as I can see here, 10 does not have any child, so we can explicitly remove this element from here. 17, 12, then 21, 19, 27, 15, 14, and 16. After deleting this 10, we have to examine whether that subtree is right now balanced or not. We have to look towards it, okay? So we have to again calculate the balance factor of each node. It will be -2 because there is no left child right now. It is 0, 0, 0, and it will be 3 and 2, it will be 1. So I can see here after deleting 10, this part has become unbalanced. Okay, this part has become unbalanced. I can see here we have removed the element from this position. Okay, so we have to see which type of rotation it will involve. We have deleted the element here. Then we have to see this type of rotation it will involve. It will involve okay, so it needs to be further revision or we need to just a second. We need to balance this subpart. Okay, we can see this part is heavy, so we have to perform the rotation into the opposite direction. That's why it will involve RR rotation. In RR rotation, there is a need of single left because this part is heavy, which is -2. It means right part is heavy. Right part is heavy, then we have to perform a single rotation into a opposite direction. So the tree will become 17. If we have to perform from this node where the unbalancing is done, it will be 17, 15, 12 will go to the left part of it. Then 16 will be here and 14 will go to the right child of 12. And then 21, then 19, and then 27. Again, I need to calculate the balance factor of each node. It will be -1, 0. It will be +1, 0, 0, 0. It will be 3 minus 2. It will be +1. Okay. Next element is 15. Now I want to delete 15. Delete 15. As I can see, if I want to delete this 15, but 15 has two children. So in this case, we have to consider the binary search tree property, where if a node which I want to delete has two child, then we have to calculate the in-order traversal. And we have to replace this element with the in-order successor of it. So in-order successor of 15 will be 16 here. So before before directly deleting 15, we have to calculate the in order successor of it, and this value needs to be replaced with the in order successor of it. Now again I have to calculate the balance factor of each node. It will be 0, -1, it will be +2, it will be 0, it will be 0, and it will be 1, 2, 3, 1, 2, it will be +1. Okay, now I can see here the unbalancing is done. If unbalancing is done, we have to look towards it. From where we have deleted this element, that was 16 was replaced there, and 15 will come here. That's why we have to perform this part. It will be LR rotation. Because this part is heavy. This part is heavy, then we have to perform the rotation into the opposite direction. Okay, this part is heavy. This is L, this is R. And we know in LR case, the rotation needs to be done into the opposite direction. It will be like this and it will be like this. Then the final tree will be, it will be 17. Then first subchild has to be done. It will be 16. Then for 16, if I want to rotate 14 on 12, it will be 14 here, then 12, because we are performing into the opposite direction, and then 12. After this, 17, 16, 14, 12, it will be 21, 19, and then 27. First part rotation has been done, then we have to perform descent, okay. Then it will be 17, it will be 14, it will be 12, it will be 16, then it will be 21, it will be 19, and it will be 27. Then we have to perform or calculate the balance factor of each node again. It will be like this. Till here, we have balanced RT. Next element which needs to be deleted, that is 17. For before deleting 17, we have to analyze 17 has two children, then we have to find out the in order successor of it, which will be 19. So 19 will come here, 17 will be replaced there, then 17 will be deleted. So the tree will be look like this: 19, which is the in order successor of 17, then 14, then 12, then 16, then 21, and then 27. Again, I'll calculate the balance factor of each node. I think the tree is right now balanced. 0, sorry, it is -1, and it will be 2 minus 2, it will be 0. So we have deleted 17 as well, and tree is balanced. No problem in this tree. Tree is not unbalanced. Again, next, the element to be deleted is 27. 27 has no child. We can directly remove 27. First of all, let us draw this tree again onto the next slide, which is 19, 14, 12, 16, 21, 27. We have to draw the tree here. 19, 14, I think 12 was there, 16 was there, 19, 14, 12, 16, and 21 and 27. Okay. And the next element to be deleted was 27. We have to delete this element. I'll write down here, delete 27. We can directly remove this element unless and until it is not affecting our tree or our tree become unbalanced. We will again calculate the balance factor of each node. I think the tree is balanced, no problem in this. Next element to be deleted is 19. Okay. 19 has two children. So we have to do if we have to find out the in order successor of it, which is 21. So 21 will come here. I'll write down here, delete 19. For before deleting 19, we have to find out the in order successor of it, which is 19. In order successor is 21. 21 will come here, then 14, then 12, and then 16. No right child. Okay, again, we will calculate the balance factor of it. It will be +2. If I can see +2, it means it is signifying that the left part is heavy. If left part is heavy, it means this type of rotation this is a LL rotation because left part is heavy. So we have to perform a single right. After performing a single right, it will become like this: 14, 21, 12, and 16 will come here. Okay. This was LL rotation in which left part is heavy. We have to perform a single right. Then 14 will come here. 21 will become the right child of it. 12 was the left child. And 16 will become the left child of 21. Okay. Next item to be deleted is, that is 12. Now I'll delete 12. delete 12. As I can see here, 12 is a single child, which is a leaf node. So first of all, we have to delete this 14, 21, and then 16. Again, I'll calculate the balance factor of each node, which is 0. It will be plus 1 and it will be minus 2. Minus 2, it means it is RL rotation because this part is heavy and there is also a sign change from plus to minus 1. In RL rotation, it will involve the two type of rotation. If left is heavy, then we have to perform into the opposite direction, which is first rotation. If right is heavy, then we have to perform into the opposite direction, which is left, and this is second type of rotation. Okay, so the tree will be 14, then 16, and then 21. This was the first step. And for the second step, we have to do this like it will be 16, and then 14, and then 21. Now we will calculate again the balance factor of each node, and we can see our tree is balanced right now. And we have deleted all the elements which was given in the question. Okay, so this was all about the deletion and insertion and what is AVL tree. We have discussed all the points. If you have doubt, or you can see the or watch the video from the beginning for getting all the concepts to get clear. Okay. In the next video, we will discuss about the B tree insertion, and B tree deletion. Okay. This is the reference which I have referred for preparing this video. Thank you, everyone.